Now let's look at sampling theory, which is another chapter. Okay, so now we are getting closer to actual applications of the probability theory that we are studying. The ultimate application is in testing of hypothesis. That's where you use all the theory learned so far to test real world hypotheses about some so when you discover a law of physics or even something simple, like you have a new piece of technology and you want to test its efficiency, you want to establish that it is more efficient than something uh, something that was used earlier, then for that also you use hypothesis testing. Okay? So when you do this, unlike in the textbook problems, you are not given information like this coin is fair, or this is the distribution followed by this random variable. That such information is not given. You just have to make observations and deduce these for yourself. But obviously, you can never have perfect information about that. So, for example, if you're given an actual coin, you don't know whether it's fair or not, unless you do some physics experiments and determine from the weights and some mathematical modeling that it's fair. There's no other way to know whether it's fair or not by just looking at it, right? So then, if you don't have that theoretical machinery to decide this, what you do is conduct experiments on it. You toss the coin many times and see whether more or less 50% of the time heads is obtained. So that will give you some assurance that indeed it is a fair coin. But again, that's never, you can never be completely sure. You can, the more experiments you do, the more certain you are. And so it approaches, the certainty approaches 100%, but never quite reaches it. Okay, so now we have to start building the theory for this. This hypothesis testing is the ultimate aim. We have to start building the theory for that. So the basic part of that is sampling theory. So sample is a word you must have heard many times. Whenever you have some statistical results quoted somewhere, you hear the word of sample. And then if you have read some research papers, for example, you might see the mention of sample size and level of significance, or the amount of certainty of the result, and so on. So the sample is mathematically just a collection of independent, identically distributed random variables, or so-called IID random variables. Okay, IID means independent, identically distributed random variables. So we'll define this in a moment. Practically, what it means is that you have some very large collection that you want to test, normally called the population. But for various practical reasons, you cannot get the information from the entire population. So it might be, you can think of the actual population of a region, for example, and you want to form some statistics about their health related statistics, for example, so some heights, weights, and eating habits, and so on. So you don't have enough resources to have a census about it. So a census means, census as opposed to sample is, census is where you interview everyone or collect the information from the entire population. So if you cannot do this, then what is the next best thing? To a sampling, right? So any survey that you do, when you fill up a survey form, for example, you send it out to as many people as you can, but that is not going to be the entire population. So you're going to use a representative subset, and ideally this should be independently chosen, correct? So if you want to talk about the or want to estimate the health parameters of the entire population of Manipal, for example, but you survey only the let's say only the people in your class. So that is definitely a subset, and that's a large subset. but that's not going to be representative at all of the general population, correct? Because that's not a random sample. There are too many other things common among this subset that you have selected. So it is not a random sample, it is not a representative sample. So you take elements randomly. So there is another theory related to how you can select randomly. If you just think of random names and do it, or randomly call numbers and do it, it's probably not going to be random, because unknown to you there are biases in you that, or in your mind, the way your mind works, that make you select according to some patterns. Okay. So there is a separate theory for how to generate things randomly, but assume that you have a machine to do that. So you select randomly from the population, and each measurement you make. So for example, if you're looking at height and call that variable x, so each particular height that you measure is also a random variable, right? You are randomly selecting an individual, measuring that individual's height. So that is a random variable x1, another is x2, another is x3, and so on. But since you are studying the entire population, all of these are identical random variables. That doesn't mean they take always the same values, then they wouldn't be random at all. They have the same distribution. So for example, if you think that the height is normally distributed with some mean and variance, then all of these are going to have the same normal distribution. Okay, when you actually observe it, you may get different values, but all of them are from the same distribution. So in effect, it is like having one random variable which you measure again and again. Although in practice you may be looking at different people, in effect that the entire set of people is being considered as one population, and this is the distribution of the population. So you are taking values at random from this, means you're repeatedly measuring values of x or making observations about it. So what you get is a sample, and if you do it randomly and independently without the one outcome affecting the other, then you have independent, identically distributed random variables. So a sample is nothing but that. So a sample is or in fact the size of the sample is important. So you say a sample is a sequence of random variables of this form which are independent and identically distributed. Okay, which means they all have the same distribution. So for example, this one is an example. Now, do you know mean and variance, the mean and variance of this? No. If you knew it, there's nothing to measure. So what you want to find are the mean and variance or other things. In fact, in this case, if you know the mean and variance, the entire distribution is determined, right? Because the normal distribution is determined by its mean and variance. So what you want to know are the mean, variance, or other parameters. But again, since you have no other way of doing it, no theoretical way, let's say, if you have a theoretical way, you can do that. If you can predict it from some other theory, you can do that. No need for statistics. Since you do not have that, only thing we can do is make measurements on this, okay, or make computations with this. So if you use these and compute anything using these values. So in general, when you compute anything with this, you can say that it's a function of this, right? For example, you may add them all up, add up all of them, or more sensibly, you can find the average value of all of these. So that looks like it might give the mean value. In fact, if I asked you to find the average of something from a population, what you would do is, again, if you cannot ask everyone, you ask a random subset, and then you will take the average of those answers and report that as the average, correct? Although it may not actually be the real average. So what you can do here is take the average or any other such measurement. So any such function of this which does not depend on these parameters. So you're measuring it only from the sample. that is called a statistic. Okay. So the word statistics is not just the name of the topic or the subject, but is the it has a particular formal definition, which means it is a function of the sample that does not depend on the parameters of the population. So the population is this. Population means a random variable, or which you are studying. Okay. So a function of the sample that does not depend on the parameters of the population, that is called a statistic. So for example, the sample mean, which is defined as summation of all the sample values, that is all the random variables here, divided by the total number or the sample size. So this n is called the sample size. So this is defined as the sample mean. So obvious definition, we know the usual definition of average. So this is just like that. This is called the sample mean. Similarly, you can define the sample variance. So that is called S square. Now there are at least two different definitions. In fact, there are two usual definitions of it. We are going to use the one in the book by Hogg and Craig, that is Introduction to Mathematical Statistics, not the definition in P.L. Mayer. Okay. So the definition we will use is 1 by square root of one by n summation xi square minus x bar square. So you can actually s square. I've written s square, so there's no square root. I'm sorry. This is s square. S, the standard deviation, the sample standard deviation, is a square root of this. So you can notice how this is similar to the definition of variance. Here you have the average of the summation of xi square. So that's just like e of x square. And here you have sample mean square. That is like e of x the whole square. Okay, but that's only a similarity. It is not, in fact, mu and sigma square. This is x bar and s square. So the difference is, again, as I told you, this is the actual population mean and population variance. Whether it's normal distribution or anything else, there is some actual population mean and population variance which you cannot know. You can only know the sample mean and sample variance. So these are things that we compute, and mu and sigma square are the true quantities which we cannot know. If you can know it, then there is no need of sampling theory. So we are starting with the assumption that for some reason you cannot actually compute mu and sigma square, or maybe you can compute, you know, one of them but not the other, anything like that. So you have some parameter which is unknown to you, and you are trying to get at it from some other computation. So this is sample mean and sample variance. So to begin with, what we will do is look at the sample mean. So as I said, this is really theory that is going to be used later. So now we'll just compute some properties of this. So let x1 etc. be a sample from a population having mean mu and variance sigma square. So these are actually unknown in practice, but suppose the mean is mu and variance is sigma square. the sample mean is defined as x bar is equal to 1 by n summation 1 to n of xi. So what I wrote just here. Then, okay, before I write this, xi, each xi is a random variable. So x1, etc., xn are all random variables because you are measuring them by, from a randomly selected individual from the population. So this is a random variable, and each random variable has the same distribution, and therefore each of them has the mean mu and variance sigma square. That is the meaning of population having mean mu variance sigma square, means each of these is having the same distribution with this mean and this variance. So if each xi is a random variable, summation of all the xi's is also a random variable, and therefore that divided by n is also a random variable. So x bar, in other words, is itself a random variable defined in terms of this. So this statistic that we define, in this case this one, is actually a random variable. Okay. Whatever statistic we define is a random variable, and therefore it has an expectation and variance. So what will be the expectation of x bar, and what will be the variance of x bar? Can we find these? The expectation is easy to find because the expectation operator is linear, right? So E of x bar, if you just apply the definition of x bar, it is 1 by n summation xi from 1 to n, I ranging from 1 to n. 1 by n is constant, and this is summation. So this immediately becomes 1 by n summation 1 to n E of xi, because of linearity of expectation, right? Now what does it say here? The mean of the population is mu. Xi is from that population, so xi has the mean mu, each xi independent of I. So this is summation 1 to n of mu itself. But what is summation of mu? Mu is a constant. So summation of mu is just mu plus mu, etc., mu n times, which means n mu. So this is 1 by n mu. So in other words, this is mu. So remember, x bar is a random variable, and if you make an observation about x bar, it could be any value. It could be anything. Means, of course, some values are more likely than others, but it could be anything because it's a random variable, right? However, if you find the average of x, or if you consider it a random variable and take the expectation of x bar, that will be equal to the population mean, which is unknown. But still, the average value of x bar is mu. Now, this has to be understood carefully. We are not saying that the average of these values is mu. That's exactly what it's not. Right, because x bar is the average of these. And we said that x bar is not the same thing as mu. In fact, x bar is not a number, it is a random variable. When you actually conduct the experiment, you will get some value, but that's a random value because this is a random variable. So it may or may not be equal to mu. What we are saying is, for that random variable, the average is mu. But what does that mean? It means if you conduct the same experiment of taking the sample, if you conduct the same experiment several times, then on the average, each time you compute this, on the average, the value you get should be mu. So on the average means if you take this sampling experiment, if you take that and repeat it many times, and every time you compute some x bar and you take the averages of all x bars, that will tend to be the true population mean. Okay. We'll understand that even more maybe when we look at variance. Now, how do you compute variance? So now you want variance of x bar. Again, remember this is not S square. I'm not talking about S square at all. I'm not talking about sample variance. I'm talking about variance of the sample mean, because the sample mean itself is a random variable. So how do you compute variance of x bar? X bar is given by this definition. Now, we can use the shortcut formula. So that tells us it is E of x bar square minus E of x bar the whole square. So this is equal to E of 1 by n summation, summation always from 1 to n, even if I don't write it later. This the square, okay, minus E of x bar we have found here, so it's the same thing, minus mu square. Hold on, I'm just thinking of how to make it easy. Oh, right. Yeah, I shouldn't have done this. We'll use the property of variance. Remember that a sample is by definition independent. So sorry, we'll directly apply this. Okay, I shouldn't have taken the definition. We'll directly use x bar. So x bar definition. So that is 1 by n summation xi. Where again this is 1 to n. Now, what do we know about variance? Variance of ax plus by, if you take, in general it is a square variance of x plus b square variance of y plus, or plus twice covariance 2ab covariance of xy. However, if x and y are independent, then this term is not there, correct? If x and y are independent random variables, this term is not there. So it's just a square v of x plus b square v of y. Now here you have summation of 1 by n, 1 by n summation of xi. Okay, 1 by n is a constant which I can take out even now before putting that inside the summation. So when the constant comes out, it becomes a square. So 1 by n square. Now variance of summation of xi. Again, remember, a sample is defined as independent, identically distributed collection of random variables. So that allows us to write this as summation of variance of xi. Okay. So this is 1 by n square summation sigma square. Again, we have summation of constant n times. So sigma square plus sigma square, etc. n times. So that is n sigma square, not n square. We are just adding up the various sigma squares. Okay, there's no squaring involved. So it is just n. So this is sigma square by n. Right. So if you define the sample mean in this way, sample mean itself is a random variable. Its expectation is mu, which is a population mean, and its variance is sigma square by n, where sigma square is the population variance. So you cannot actually measure mu and sigma square, but the sample mean as a statistic is a random variable, whose mean and variance are given in terms of these. Okay, again, you cannot truly know the mean or variance of x bar itself. In an experiment, you cannot actually find the mean and variance of x bar itself. Otherwise, you could know these quantities. This is also something that you cannot discover by experiment. Right? Expectation and variance are not something you can compute by experiment unless you have some finite data set, which is not the case. This is a random variable. But the theory still holds. And what does this tell you intuitively? Firstly, as I said, when you conduct this experiment and find this x bar, although it may or may not be equal to mu, on the average it will be. Which means if you do it several times, or if many people do the same experiment, on the average you will get around the same value of mu. All the values that you get will be on the average mu. Further, what does the variance tell you about the random variable? How much the data is spread out, right? So again, x bar has variance sigma square by n, which means not only is the average value of x bar going to be mu, also the deviation of this actual value of x bar from this mean value, which is equal to the population mean, that deviation is going to be proportional to this sigma square by n. Well, the deviation is in some way equal to sigma square by n. So if you take a larger sample, that is if this n is large, then this variance is going to be very small, which means more often you will get a value very close to the population mean. So if you have a very large population and you want to estimate its mean, if you want to improve the value that you get, if you want to be more certain that the value that you get is closer to the actual population mean, take a large sample. So the larger the sample, the better your estimate of the population mean. The intention of using the sample mean is usually to estimate the population mean. So the larger your sample, the better your estimate. That's what this says. And also, the larger the variance of the population, the worse your estimate, because the sigma square is in the numerator. So if the population variance itself is large, that means clearly, what does that mean? That each x1 is bound to deviate a lot from its mean. So if you find several xi's and take their mean, that's still not going to be very close to the actual mean, right? Because each random variable is deviating a lot from its mean. So if the population variance is large, this is not going to be a good estimate. Or in other words, if you want to make it a good estimate, you have to take a very large sample size. Again, these are things you cannot know, or maybe you know only mu and not sigma square. That's possible. That in some cases you know mu, you don't know mu, but you know sigma square from some theoretical considerations. In that case, according to that, you can take a large enough sample size. That's also there. So the intuitive part of this also should be clear once we get these answers. Right? The larger the sample, the better your results. That's something you already know. Intuitively, you know this. That's what this theory says. So then, once you have this still does not tell us what exactly is this distribution. But in the case of a normal distribution, you know, suppose this xi itself has a normal distribution. Right? Suppose x itself has a normal distribution, which very often is the case. In large populations, you can always approximate it by normal distribution. Then we know from the reproductive property of the normal distribution that a sum of normal variates is also normal. And here you have its mean and variance. So in this case, x bar is going to be also a normal random variable with mean the same and variance sigma square by n. That's a special case. Now later when we study central limit theorem, what we learn is if n is large enough, then this doesn't have to have normal distribution. Whatever distribution this has, this will still be approximately normal. Just like in a large binomial distribution with large n and small p, it is approximately Poisson. Like that, whatever be the distribution of x, If the n is large, if the sample size is large, then the sample mean will approximately have a normal distribution with this mean and this variance. So based on this, we'll do some problems next time.